A lecture on gravity, Part B, bringing it all together. Newton's explanation of the motion of planets and orbital motion in general. Isaac Newton's theory of gravity, or law of gravity, is that two masses attract each other dependent on the distance they are apart. The equation F is the force of gravity, equaling capital M lowercase m, the amount of inertia for each object, or the amount of matter or mass, divided by d squared, the separation between the center of masses of the two objects squared. Capital G is the gravitational constant that relates mass, distance, and force. Its value is 6.67 times 10 to the negative 11th in the units of the SI, Standard International MKS units that we use, meters, kilograms, and seconds. Work out what the units of G must be using meters, kilograms, and newtons for the units of force, mass, and distance respectively. G is an extremely small number in these units. So here we see from your text two masses, mass 1 and mass 2. They attract each other, all masses, whether it's planets, stars, moons, balls, or even two people, have a gravitational attraction simply because they have matter. Two masses attract each other, depending on the amount of mass they have, the product of m1 times m2, and the distance r that they are apart. And by Newton's third law, the force of mass 2 on mass 1 is equal to the force of mass 1 on mass 2, equal and opposite forces for the force of gravitation. The force of gravitation follows the same rules as any contact force. It follows the third law of equal and opposite forces of gravitation, and a gravitational force, if balanced out, will follow Newton's first law, and if a gravitational force is unbalanced, then it will follow Newton's second law to accelerate the object. What does it mean for the gravitational force to be dependent on the distance squared? Well, if two objects are a distance apart, there's a certain attraction of gravity. If we double the distance that the objects are apart, the gravitational attraction is a fourth while doubling the distance. If we triple the distance, the gravitational attraction is 1/9. Thus, the gravitational force drops off rapidly with distance. How do we determine the value of G? A famous experiment by Cavendish over 100 years ago had two large masses, a lead sphere and a small connected to a small masses connected on a rod, attracting a large lead sphere. So two ordinary sized masses were used, and the attraction between them, the gravitational attraction between them, was measured. The two masses on a rod would twist towards the lead spheres, towards the lead balls. The amount of twist, the amount of twist was measured. In essence, what has happened is the twisting is measured in the same way that the stretching or compression of a spring would be measured. How much twist was determined by the force of gravity. So you can take two masses on either end of a spring and see how much they compress the spring. But it's a little bit easier to measure two masses twisting a thread as they are attracted to the two lead spheres in the illustration. So you can measure the amount of twist, you can measure the amount of mass, you can measure the distance that the masses are apart, and you can measure the amount of twisting, and from this you can determine the only one unknown, the gravitational constant. It's a very difficult experiment to do, but it was done, and the gravitational constant was determined. Since then, we've done other types of experiments on much greater scales and with much greater precision, consistently getting a value of the gravitational constant G. This doesn't work. This works for objects like lead spheres on the Earth, for small masses and large masses, for objects that are thrown around the Earth. such as satellites from the moon attracting to the Earth. So in this illustration, say we have some mass that's going around a massive planet like the Earth, and the lowercase m could be the moon, the uppercase m could be the Earth. The small mass is going around in a circular orbit around the large mass, say the moon going around the Earth, pretending to be in a circular orbit. Well, we know that an object going around, say the two masses are attracting each other by the gravitational force, Fm on m. If the small mass has a tangential velocity, and the gravitational force is perpendicular to that tangential velocity, then it'll be going around in a uniform circular motion. It'll be constantly changing the direction of the small mass, as it goes around the large mass. If it constantly changes the direction, but doesn't change the speed, then this is a radial or centripetal force, which would go around the same way as a ball on a string. Therefore, the gravitational force, mg, could be the same as a radial force, mv squared over r. So the moon going around the Earth would be the same as any object, such as a ball going around in a circle, being whipped around not by the tension of the string, but being whipped around by the force of gravity. So rules found for ordinary objects, such as the tension whipping a ball in a string in a perfect circle, could work the same for objects in the heavens. The Earth could whip the moon around in a perfect circle, or a satellite in a perfect circle, by the gravitational force acting as the tension, whipping the object around with a radial force subject to the relationship mv squared over r. So let's say we have a planet and a star, such as the Earth and the Sun. So whether we're talking about the force of a string or the force of gravity pulling planets in circular orbits, the physics is the same. Thus, for the orbiting body, the gravitational force is a radial Fr, or centripetal, force. So Newton's law of gravity can be used to describe a centripetal force. So therefore, the centripetal force follows the Newton's second law, mv squared over r. Now we equate Newton's law of gravity, gmm over r squared, to equal mv squared over r, canceling the mass and rearranging for the velocity. We get the velocity to be related to the gravitational constant g, the mass of the planet, the mass of the sun, the mass of the Earth, the mass of the object that's whipping around the smaller mass in its circle, divided by the distance, the radius of the circle. Thus, we can determine the orbital speed of a satellite, the orbital speed of the moon around the Earth, or the orbital speed of any object going around in a circular orbit. Newton's laws work for balls on strings. Newton's laws work for objects on the Earth. Newton's laws work for objects falling to the Earth. Newton's laws work for the moon's orbit about the Earth, the Earth's orbit about the sun, the International Space Station, satellites orbiting the Earth, any planet about the sun, any planet about a star. Newton's laws of motion, including the gravitational law, work for binary stars and other solar systems, and stars orbiting in a galaxy. Newton's laws work for all objects on the Earth, whether mundane or gigantic, and all objects in the heavens. Newton's laws, all objects are subject to the same laws of motion. The only exception seems to be that stars going around in the giant galaxies, the giant collections of hundreds of billions of stars, such as our own Milky Way galaxy, the stars go around the galaxy following Newton's laws, but stars far out on the edge don't seem to follow Newton's laws. Either Newton's laws are wrong for galaxy-sized objects and stars far at the edge, or there has to be missing matter that would account for the missing gravitational pull. This is the story of dark matter. You can read more about dark matter in the lecture notes. Distinguishing between big G and lowercase g. Big G, the gravitational constant, versus lowercase g, gravitational acceleration. From a planetary perspective, lowercase g is surface, the gravitational acceleration at the surface. That's what we've been using. 9.8 meters per second is the gravitational acceleration at the surface of the Earth. This is what we use in F equals mg. Capital G is the gravitational constant that relates masses over distances to forces. It's a universal perspective. Gravitational G, capital G, is a constant as far as we know throughout the universe, whereas lowercase g is an acceleration at the surface of the Earth. It's different higher up, it's different lower down, it's different on other planets, and it's different at different locations throughout the universe. Relating F equals mg to F equals g mm over r squared, we get lowercase g, acceleration, is equal to capital G, the gravitational constant, times mass divided by r squared. So what this tells us is g varies with the mass of the planet and the radius of the planet. The capital G is always constant. So a 10,000 Newton astronaut standing on a planet of size radius r has a particular gravitational acceleration or particular weight, mg. If for some reason this planet shrunk to half of its size, half the radius, well, then capital G is always constant, it does not change, but lowercase g, the gravitational acceleration, is increased. Since the gravitational acceleration depends on r squared, and r is now half the size, then the gravitational acceleration is half r squared, or 1/4 the gravitational acceleration. Therefore, he's now 4 times as heavy. 1/4 r squared on bottom gives you a ratio 4 times as great, 4 times the gravitational acceleration, therefore 4 times the gravitational weight, from 10,000 newtons to 40,000 newtons for this astronaut on this shrinking object. This would be similar to the idea of a black hole. If the star or object keeps on shrinking, the gravitational acceleration and the weight increases until it goes to infinity as the object shrinks down to the size of 0. So we see gravity depends on mass and size. Gravitational acceleration depends on the mass divided by r squared, the size of the planet or the star. For instance, Saturn is 95.16 times as massive as the Earth. But local G near its surface is 10.5 newtons per kilogram, which is about the same as on Earth, 9.8. They are both about 10 newtons per kilogram, even though Saturn is almost 100 times larger. Because the diameter is 11 times larger, but the density is so much less, the gravitational acceleration works out to be about the same. It's much more massive, right? Almost 100 times as massive, but the diameter being 11 times larger gives you a ratio that's roughly the same. Mass divided by r squared, a mass of 95 times greater